Okay, when we're solving problems using free body diagrams and forces, we need to be able to identify all of the forces that are acting. So in this video, I'm going to talk about a couple of the more common forces that we'll see and their general properties. This is not going to go into all the forces in detail, but it should help us to identify when the force is acting and how does the force work. So let's take a look. First of all, our most important force is gravity. F sub g, or mg, is the equation for gravity, where m is the mass and g is the acceleration due to gravity or gravitational field strength. Gravity is an attractive force between all massive objects in the universe. If we're thinking about it in a cosmic scale, our formula is a little different, but if we're thinking about it on a planet like the Earth or on a moon, it's just a constant force that pulls objects down towards the center of the planet or the moon. So if we toss an object through the air, what is the free body diagram for it? If there's no air resistance, while gravity is still pulling on it, gravity pulls straight down. So it's going to be a downward force vector. And since the force of gravity is constant, if we draw that free body diagram in different locations, that force vector is going to be the same length. And we can label it mg, or we could label it as F sub g. We could also label it as W, because the force of gravity is also called weight. The weight of an object is the force of gravity on it. Air resistance, or fluid drag, is a force that happens when an object moves through a fluid. And what happens when we move through a fluid is we are going to be bumping into a bunch of air molecules or water molecules or fluid molecules. And every molecule you bump into is going to apply a force to you, therefore pushing back on you, resisting your motion, slowing you down. So the drag force acts whenever an object's moving through a fluid, and it's always going to act opposite the direction that the object is moving. So if our velocity is to the left, our force is going to be to the right, our drag force. The other property of drag is that drag gets stronger the faster the object is moving. So if we drop an object, it's not moving, there's no drag force. My free body diagram, right when I drop it, when it's not moving, is just mg pulls down. But once it starts moving in the downward direction, you can see that over here, a drag force starts to act opposite the direction of the motion. Gravity's still pulling down, it's just that the drag force is now partially canceling it out. So important property is it's always opposite the velocity, and it gets stronger at greater speeds. A projectile thrown in the absence of air resistance, let's draw the free body diagram. If it's thrown horizontally, let's just sketch out the trajectory. Well, initially, it's going to be moving to the right. And so in the absence of air resistance, the only force acting after we release it is going to be gravity, force of gravity. If it's over here, having fallen a bit, there's still no air resistance, so the only force is still the force of gravity. What happens when there is significant air resistance? Well, there's going to be a force that's opposite the direction of motion. So initially it's moving to the right, so there's going to be a leftward drag force. At this point over here, the velocity is down and to the right, so there's going to be a drag force that is up and to the left, force of drag. The normal force is a contact force that acts between solid objects that are touching each other. And it's the push between solid objects. Push between solid objects. That's supposed to be an underline. It's the force that's just going to be strong enough to prevent objects from falling through each other. You feel a normal force all the time. If you're standing on the ground, gravity is pulling you down. Why don't you move down? Well, because the floor is in the way, meaning the floor has to be pushing up on you with a force that's equal to gravity, or at least equal to gravity. It's called the normal force because normal means 90 degrees to a surface. And the direction of the normal force is always perpendicular to the surface, or 90 degrees to a surface. So if you're on a slope, the normal force points up at an angle to that slope, at 90 degrees to that slope. And it's just going to push as hard as necessary to prevent you from moving through the object. How about this? We have a person in the elevator, and the elevator is accelerating up. Let's draw a free body diagram for them. So I'm going to sketch out a box to represent the person. And what forces are acting? Well, gravity is always acting, so I'm going to draw that. Force of gravity is down. And are we accelerating or in equilibrium? Well, we're accelerating up. It tells us that here. If we're accelerating up, that means our net force must be up. Since we're touching the floor, there's a normal force from the floor. And since our net force is up, that means that normal force is going to be bigger than gravity. We can call it N. We could call it F sub N. The net force points up, leading to an upwards acceleration. Friction is the other contact force that acts between solid objects. And friction is the force that acts parallel to the plane. So you know what friction is. If you slide two objects across each other, friction is going to try and slow those objects down. It's going to resist sliding motion. So if you have an object that's sliding, like this human that's diving across the ground, friction is going to act opposite the direction of the sliding motion. Their velocity is to the left, so friction pushes to the right. But friction can also push you forward. If you're walking, you place your foot on the ground and you try to push your foot backwards. You try to slide it backwards with a backwards velocity. Friction doesn't want you to slide, so it's going to apply a forward force to you. And it's that forward force of friction that allows us to propel ourselves forward. It's also what propels car tires forward. So it's going to resist sliding motion. It can either slow down the sliding or it can completely prevent sliding motion. So if we have a car braking on a horizontal road and the tires aren't slipping, let's draw the free body diagram. I'm going to sketch out a quick car. This is a little bit more detailed than most free body diagrams. What forces are acting? Well, gravity is pulling down on the car. Force of gravity. Our car is moving to the right, so it's got a rightward velocity, and it's braking. That means it's slowing down, so the acceleration is going to be to the left. So what other forces are acting? Well, each of my tires is on the ground, so each one's going to feel a normal force. And the total normal force is going to cancel out gravity. But also I'm braking, meaning friction is going to try to slow me down, so there's going to be a leftward frictional force on each tire. And that's my free body diagram. Net force is to the left. I could also do a simpler version of this diagram. I could just draw the forces without applying them to the correct points, and I'd get gravity down, I'd get the normal force up, and I'd get friction to the left. An applied force is just a force from a person or a machine. Technically, an applied force might also be called a normal force or some other type of force, but it's usually just a general name we give to a force from a person or a machine. So here we have two football players colliding. Player A dives and tackles player B. So this must be player A on the left. This must be player B. What is the free body diagram for player B while they're being hit? Well, player B is feeling gravity down, force of gravity. They're on the ground, so they're feeling a normal force cancel that. And A is pushing them, and it's pushing them to the right. So there's going to be an applied force from A. What's the free body diagram for player A while they're tackling player B? Well, player A is in the air, mostly in the air. They're still feeling gravity, though, so there's going to be a downward force of gravity. And, well, they're moving to the right, but when they collide with that person, they're going to slow down, meaning they're going to feel a leftward acceleration. So they're actually feeling a force from player B, and we could call that also an applied force from player B. In that collision, they're both feeling forces. They're both pushing on each other. Tension is a force from a taut string or a rope or a cable. If you pull on a string and it tenses up, it applies a force. And it always pulls parallel to the length of the string. And the tension is going to be constant throughout the entire rope, at least in steady state for our intro purposes. The free body diagram for a chandelier hanging from two vertical ropes is given below. Gravity pulls down, and there's one tension force at each rope. These two tensions together have to cancel out gravity. Let's draw a free body diagram for a pendulum bob at its highest and lowest points. Well, a pendulum bob is just a mass on a string. That string attached to a pivot point. Whoops, we skipped forward. So here's our pendulum bob. We know it's feeling gravity. And the tension force is going to be in the direction of the rope, the direction that the rope pulls. So there is a force of tension in this direction at the highest point. The net force is not zero because these don't exactly cancel each other out. They're not in opposite directions. What about at the lowest point? Well, gravity's still going to act, force of gravity. And since we're still going to be attached to a string, there's still going to be a tension force upward. For reasons that we'll talk about later, because it's changing its velocity's direction, these forces don't actually cancel out. Tension's a little bit bigger, but those are the forces. What about a free body diagram for the point on the rope where the bird sits? The rope is motionless. Well, the point on the rope is feeling a downward force from the weight of the bird, so I'll call that W. And there's a tension from the right side of the string pulling this way, and a tension from the left side of the string pulling this way. Call them both T. It's not the most accurate drawing ever, but we know since the rope is not moving, the horizontal components of these forces have to cancel, and the vertical components of the two tensions have to cancel out the weight. The spring force or the elastic force is a force from a spring or an elastic surface. What happens with a spring is if you compress it, if you move it to the left, for example, it's going to try and push back to its equilibrium position, push back to the right. So if you compress it to the left, it's going to push back to the right. If you extend it to the right, it's going to pull back to the left towards its equilibrium position. And so the spring force or elastic force is always going to push in a direction back towards the equilibrium. This is a displacement to the left. That's all. Bye.